In this section, we'll look at the last two convergence tests, the ratio test and the root test. And we'll start off with the ratio test. If we have a series with non-zero terms, then that series converges absolutely if the limit of the ratio between two consecutive terms, its absolute value, is less than 1. It will diverge if the ratio between two consecutive terms is greater than 1 as n goes to infinity, or if that ratio is infinity. And the test is inconclusive if the limit of that ratio is equal to 1. So we want to know, does this converge? And we're going to use the ratio test to do this. So a sub n would be 2 to the n over n factorial. A sub n plus 1 would be 2 to the n plus 1 over n plus 1 factorial. Now to perform the test. And since I'll be taking a sub n plus 1 and dividing by a sub n, that's the same as multiplying by the reciprocal. And if the factorial and the power could cancel out, this would be a very easy limit to evaluate. And that is exactly what happens, because this is 2 times 2 to the n over n plus 1 times n factorial. And this is equal to 0. So our series, 2 to the n over n factorial, converges absolutely. By the ratio test. Now I have n to the n over n factorial. So I'm going to take the n plus 1 term, and divide or multiply by the reciprocal of the a sub n term. Again, my hope is that the power piece of this will cancel, as will the factorial. And with some simplifying, we see that some stuff does cancel. And what I'm left with is n plus 1 to the n over n to the n. And that power didn't cancel. And since n is always positive, I don't need the absolute values anymore. And this can actually be rewritten into a limit that we know. The limit of 1 plus 1 over n to the nth power, which is equal to e. So by the ratio test, this series diverges because e is greater than 1. This next one we have an alternating series. And we're going to start by looking at what the ratio test does for us. And now I perform the test now that I've identified the n plus 1 term. And since I'm dealing with absolute values, I can ignore the negative 1 to a power piece of this. And as n goes to infinity, what we're left with is the square root of 1 times 1, which is equal to 1. So this ratio test is inconclusive. So we have to go to a different test, and you might have been thinking, well, why don't you just use the alternating series test? I wanted to show you how the ratio test could be inconclusive. So now I'm going to go to the alternating series test. And with that one, remember we take the limit as n goes to infinity of the square root of n over n plus 1. That needs to equal 0. And doing some simplifying, we're using L'Hopital's rule. This will be equivalent to the limit of the derivative of the top divided by the derivative of the bottom. So that's a limit of 1/2 n to the negative 1/2, and that's equal to 0. Now I have to show that a sub n plus 1 is less than or equal to a sub n. And I'm going to do this using calculus. I'm going to show that this is decreasing, meaning the first derivative needs to be less than 0, needs to be negative. So I can think of this function, this rule, square root of n over n plus 1 as square root of x over x plus 1, and I find the derivative. Using the product rule, I get x plus 1 times 1/2 x to the negative 1/2 minus square root of x over x plus 1 squared. And then, in order to simplify this, I want to essentially get a common denominator on the top, because the first term is x plus 1 over 2 times square root of x. So I'm going to multiply top and bottom of the second term by that. And what I'm left with is going to be x plus 1 minus 2x over 2 square root x. And so my derivative in simplest form would be negative x plus 1 divided by 2 square root x times x plus 1 squared. And for this, because x is always a positive number with this series, f prime of x, the derivative is always less than 0, thus f of x decreasing. So by the alternating series test, our series converges. But the question now becomes, does this converge absolutely or not? The ratio test would have told us if it converged absolutely. I don't know yet. So now I want to look at the absolute value of this alternating series. So I'm looking at n equals 1 to infinity of square root of n over n plus 1. I'm going to do a direct comparison. And if I look at square root of n over n, that would be 1 over square root of n, which is a divergent p-series. And for this, the square root of n over n plus 1 is greater than or equal to 1 over the square root of n for all n. I take that back. I'm not doing a direct comparison. I'm going to do a limit comparison. So I'm taking square root of n over n plus 1 divided by 1 over square root n. This simplifies to n over n plus 1, and this is equal to 1. So since this quotient of the two rules gives, and I take its limit, is equal to a finite positive number, and since what I'm comparing to diverges, my series will also diverge. So going back to the original rule here, it converges conditionally. For the last test, we're going to look at the nth root test. And if we have a series, it will converge absolutely if we take the nth root of the rule and get a number less than 1. It will diverge if the nth root, the limit of that, is greater than 1 or equal to 0, or infinity, And it's inconclusive, again, if that nth root limit is equal to 1. So you might imagine that this test is useful if we have things to the nth power, where in this one we do. So I'm going to use the nth root test, limit as n goes to infinity of the nth root of this rule. So I have e squared over n, and that limit is equal to 0. Since 0 is less than 1, our series converges absolutely. Some guidelines for doing these tests. First, does the nth term tend to 0? If it doesn't, we have that nth term test telling us that the series diverges. If it does tend to 0, we need to do more work. And the easiest tests to look at are the geometric, if it's geometric, or if it's a p-series, or if it's a telescoping or alternating series. Those are probably the simplest tests to apply. If our rule doesn't fit with one of those situations, can we use the integral, root, or ratio test effectively? And if those don't work, can we do a comparison? Reason comparison is last here, I think, is because there's a lot of different things you could compare to. And you kind of have to pick and choose to find one that works the best. So you now have all the tests for checking to see if a series is convergent or not.